So, in today's kinematic lecture, we are going to learn about projectile motion. If you follow this lecture, you should be able to crack all the projectile motion problems. So, let's learn about what is a projectile motion. So, if you are throwing a ball like this at an angle making theta with the horizontal, this ball or this point will follow a path something like this, and this is called the projectile motion. This I am calling as x-axis and this is y-axis, and the initial velocity is u making an angle theta. So these are the things given: an initial velocity, an angle with the horizontal, and that's it. And you need to find out few things. We will derive the equations for these things, and more important than the equation itself is the way we are going to solve it, because that's the principle you will be using in every single problem. The principles are very simple, really very simple. So what are the things we need to find? If you notice, this projectile, when it's making a projectile motion, it will reach a maximum height at some point of time. We need to find out what is this maximum height. Number one, this is projectile motion lecture, and in this projectile motion lecture, the first thing we need to find out is max height, called h. Now you notice that if we try to throw it with a higher velocity, it's going to have a higher height. If we throw it with a smaller velocity, it will reach less height. If we make an angle that is more, then the maximum height will be higher. If we throw vertically upward with the same velocity, it will reach the maximum height. And if we just throw it like at a lower angle, it will reach a very less height. So this is a dependency of maximum height with u and t. But what is that exact value? The second thing we need to find is time of flight. When you throw it, it reaches the maximum height and comes back. What is the time it takes to hit the ground again? Obviously, again, if you throw it with a higher velocity, initial velocity, it will take longer to reach to the ground back. Third thing we need to find is the range. We call the range as, this is the r is the range. Now we are going to solve it in as simple steps as possible. Here is the two basic principles you need to do. You resolve this velocity in two parts, a horizontal part and a vertical part. The horizontal part has a component u cos theta, and the vertical part has the component u sin theta. Separate these two things and the life will be easier. Divide and conquer. What is happening in the u cos theta direction? The u cos theta is a velocity, is a component. There is no acceleration working against this velocity. There is nothing that is either reducing this velocity or increasing this velocity. It's constant throughout the motion of this path. What about the vertical velocity? The vertical velocity u sin theta is working against the force of the gravity. This velocity is not constant all along the path. The effect of the gravity reduces it as it moves along. So let's say we are at this point. The horizontal velocity u cos theta, it is still the same. There is nothing, no force acting on it. But the vertical velocity, which was this much, it gets reduced because of the acceleration of the gravity working on it. Then it comes here. The horizontal velocity is still the same. The vertical velocity is further reduces. At this point, the horizontal velocity is still the same, u cos theta, but this velocity, the vertical velocity, is 0. When it goes down, the horizontal velocity is still same. The vertical velocity is now acquires a downward direction because of the gravity, and so on and so forth. And finally it reaches the x-axis. The horizontal velocity is still u cos theta, and the vertical velocity has some value. We'll find that out. So that is what happening in this whole projectile motion. So let us try to find out this maximum height, and we have this formula: v square is equal to u square plus 2gh. We will again use this high school formula. We are not doing anything new here. But one thing we are doing, and that we probably have learned in the vector chapter, of resolution of this vector. That is new thing. If we apply this formula in this path, in the vertical direction, forget about the horizontal thing. In the vertical direction, we have this final velocity, final vertical velocity is 0 here. So we put 0 here. Initial vertical velocity is u sine theta. So you put u sine theta whole square. The acceleration is working against it, so we have minus g, so 2g. And this height here we are calling a big H, a capital H, and that is our maximum height. And from here we have the maximum height of the projectile motion as u square sine square theta divided by 2g. Our first problem is solved of maximum height h. You see that how the separation of the horizontal and the vertical things, it helps us solve these our problems. Let's move on to the next one. The time of flight. And in this one, we are using this formula: S is equal to ut plus half a t square. This is one formula. We will use the other formula also. Now, what happened when we have thrown this with u velocity, and let's again consider the vertical displacement. When it starts from here and reach here, what is the vertical displacement? It is maximum here, but again it becomes 0 here. So I can write for the vertical motion between this point and this point, displacement is 0. What is the vertical velocity here? U sine theta into t, and a is minus g, so this is half g t square. There is 2 t's, don't cut it yet, just understand it. T multiplied by u sine theta minus 1 upon 2g into t is equal to 0. This condition is satisfied, that is the vertical displacement is 0 at 2 times. When t is equal to 0, obviously this vertical displacement is 0 because they have not yet moved. But there is another condition of g where this thing becomes 0, and that happens when half gt is equal to u sine theta, or t is equal to 2u sine theta divided by g. And what is this? This is our time of flight t. Instead of t, let us write capital T to denote time of flight. So we have solved these two problems with very simple principle of resolving the horizontal and the vertical components. And then we need to find out this range. And here comes the third and a very simple use. And a principle that the time t stays same whether in a path at certain point of time, whether you take the vertical thing or the horizontal thing. So consider this range, this path from here to here. It took time t is equal to 2u sine theta multiplied by g. This is the time it will take to make this horizontal movement. So if I need to find this range r, this will be equal to this constant velocity u cos theta, multiplied by u cos theta multiplied by this time t, which is the range, that is the time it takes from come to here to here. Now if I substitute this value of t here, what do we get? U cos theta multiplied by 2u sine theta divided by g. So we have taken this formula, substituted it here, so I can remove these things. There is some simplification here. U into u is u square. 2 sine theta into cos theta is sine 2 theta, and this whole thing divided by g. This is our range formula. So we have derived all those three formulas using very simple principle of resolving the velocity in vertical and horizontal directions, and lastly combining the time. Both the vertical and horizontal movements are combined by the time. Now this another question we ask is, when is r maximum? If you are given a given velocity u, you cannot throw a ball, a shot put ball, more than a certain speed. What can you do to maximize this speed? At what angle should you throw the ball so that it reaches the maximum? This sine 2 theta, the max value of sine 2 theta is 1. It cannot be more than 1. And that happens when 2 theta is equal to pi by 2. Because sine pi by 2 is 1. Or this happens when theta is equal to pi by 4 or 45 degree. So if you want to achieve a maximum range, you should throw it with 45 degrees. So the graph will look like this. If you throw it by 45 degree, you reach this range. If you throw it with a lower angle, this is 45 degree. If you throw it at a lower angle, it reaches here. If you throw it at a higher angle, then also it reaches the lower range. The maximum range is achieved at 45 degrees angles. In part B of this lecture, we will do some problems on the projectile motions. Make sure you try to solve all of the problems on the projectile motions, and don't memorize this formula, derive it on the spot and use this resolution of horizontal and vector vertical components of this initial velocity.